Hello everyone, welcome to my YouTube channel. So I am going to solve the second part of Tifr Gs 2022 solution. It is basically true false section. Okay, okay. So the first question says that there exists no monotone function f from R to R which is a discontinuous at every rational number. Okay, which is discontinuous at every rational number. So this video you can just go to my interesting problem section okay, problem section playlist, and there is a video named on that discontinuities of monotone function. Okay, there I have already discussed this thing. So problem number two. So we know let f g be two continuous function on R such that f restricted on Q is same as g restricted on Q, right? That means f equal to g for all x belongs to Q. Since Q is dense, then f equal to g identically. It's a basic real analysis fact, right? So I'm going to use this. We know that Q is countable. That means Q is similar to natural number, where natural number is also countable. So I can think the element of Q as a sequence, because natural number, I can think natural number to be a sequence. So I can also think Q to be a sequence, right? Then I can define n. Say this is the bijection from Q to n. The most easy one is that let psi be the bijection. Okay. Then take f. Okay. Take f and define f of psi inverse 1, comma f of psi inverse 2, comma so on as a sequence. Now if image of f and g are same, so on. This is the sequence, right? So if image of f and g are same, that means f equal to g on Q, because here all the rational number already we are counting, right? So f equal to g on Q, that will imply that f equal to g on R. That means this map is injective. This phi is injective. Hence phi is injective. Okay. Problem number 3 is very easy. Basic sequence fact. Basic fact from sequence. So you can easily do that. I leave it as an exercise. Okay, problem number 4, I am not going to discuss it because the similar concept question also came in the 2019 paper also. So I will make a separate video for this. I have already mentioned in the last video the same thing, that is a Stone-Weierstrass theorem. Okay, I will particularly make a video particularly on this topic, and I will discuss applications of this, and this is also an application for that. Now starts nice problems from question number 5. So 5. If x is a metric space such that every continuous function f from x to R is uniformly continuous, then x is compact. See, if you have f from x to r, okay, and x is discrete metric space, then any map is continuous, right? Because in discrete metric space every set is open, so inverse image of open set is automatically open, so any function is continuous. So take a infinite discrete metric space, infinite discrete metric space, take, and we know that infinite discrete metric space is not compact, because you can write x as the union of singleton, the singletons are open here, right? And this doesn't have any finite subcover since x is infinite, cardinality of x is infinite, so it's easy. Now any function is continuous, and as well as uniformly continuous also. Any function is continuous as well as uniformly continuous. Why? Because see, let epsilon greater than 0 be given, choose delta to be half, then fx minus fy, sorry, f distance of fx comma fy, distance of x comma y less than half. Whenever distance of x comma y less than half, that will imply x equal to y, because distance of x comma y is either 1 or half, or 0, sorry, distance of x comma y is either 1 or 0. Then distance of x comma y is less than half means x equal to y, and x equal to y means fx equal to fy. That means distance of fx comma fy is 0, which is always less than epsilon. Then for any given epsilon you can just particularly choose delta to be half, then it satisfies. That means it is uniformly continuous. So every continuous function, every function is continuous as well as uniformly continuous. So every continuous function is uniformly continuous, okay, but x is not compact because x is infinite discrete metric space. So this is nice one. 6. This is this problem I have solved in a different way. So if you have another any different solution, you can just tell me. Okay, this is so let Cx denote R vector space of continuous real valued function. Okay, Cx denote R vector space of continuous real valued function. Let x is finite, right? X is finite. That means any map is continuous, right? That means any map is continuous. Map is continuous. That means in that case cardinality of Cx is this, right? And you can write Cx as, say, any element of Cx, say f belongs to Cx, so you can write it as f of x1 comma f of x2, f of, say, xk, and so on, such that this tuples belongs to R power order of x, right? So that means dimension of Cx is order of x. It is easy to check. Dimension of Cx is order of x because I can write it as a order of x tuple, right? Every element of f can be written as this because x is finite, so f is determined by its values on each point, and so I can just write it as a tuple, f of x1, f of x2, f of xk, and so on, where this tuple belongs to R power order of x, right? Now let x is infinite and a subset of x be a finite subset. Okay, now I am defining, I can define an obvious map from this to this, So T, where T of F equal to F restricted on A. And T is linear clearly. Right? T is linear by definition. Now since A is closed, A is finite, so A is closed. So by T's extension theorem, any F from A to R can be extended as a continuous function from X to R. That means T is surjective. This implies T is surjective, because if you choose any continuous function from here, you can always extend it as a continuous function from X to R, right? So T is surjective. Then dimension of Cx, because it is surjective, so dimension of Cx is greater or equal to dimension of C of A. And A is finite, so dimension of C of A is same as order of A. Now if X is infinite, you can choose any finite order set, so that means dimension of Cx is greater or equal to n for every n. This will imply dimension of Cx is infinite over R is infinite. So very nice problem. So this is a very strong result, T's extension theorem. You need to use that. Question number 7. Okay. Okay. So this Rn minus countable union of lines or subspace or anything like that, I will make a separate video for this, because a very important concept. Okay, I'll make a separate video for this, because I need to explain it a lot, because the same type of question comes many times, like R2 minus Q2 or R2 minus countable many points, all things. Okay, so here R3 minus countably many lines. Problem number 8. An invertible linear map from R2 to itself takes parallel lines to parallel lines. Right. So parallel line means what? Parallel line means what? So you can say you have this R2, right? Say this is R2. So you have these two lines. These are parallel, right? These are parallel all R. So that means you can fix up. So that means L1 can be written as x plus lambda. If this is lambda times, I should write it as, I mean, I want to mention it's a x1 times lambda y1. No, I don't think it is the equation. Better to write it as I want to say that what I want to say. Let's first write the equation of a line in R2. Okay, so it's better to write, say L1 is denoted by y1 equal to mx1 plus c1, y2 equal to mx2 plus c2, right? Why? Because you know, right? Because these are parallel, so both have same m. M is same. Here it is m1 m2, m1 equal to m2. And if you map it, same as m times t of x1 plus t of c1, and here it is t of y2 is m times t of x2 plus t of c2 by definition. Here also m are same. That means they are parallel. So T of L1 and T of L2 is also parallel. T of L1 is T of L2, both are parallel. So any linear map do this. Okay, uh, but one thing can happen, that since it is invertible, so dimension cannot be less. So it maps a line to precisely a line, because otherwise it may happen that it can map one line to 0. Right here it may happen that T of C2 is 0 and T of X2 is also 0 for all X2. Then this will be identically 0. But that will not happen because of it is an invertible map. Okay, that means it maps line to precisely the line. Okay, and since both have same M, after applying linear transformation due to linearity, both have same. So M will be same. Like M1 equal to M2 equal to M here. Okay, so this is 8. So invertibility only important here because of the thing is that, so line cannot be a point. That is the importance, nothing else. Okay, but if but only thing that it sends parallel line to parallel line, that depends on the linearity property, nothing else. But since it is invertible, it maps line to line. That is important. Otherwise it may have that it maps line to a point. So to exclude that condition, I need invertibility. Okay, go to the next one. Problem number 9. This is just an application of Jordan canonical form. So for any matrix C, MC denotes the minimal polynomial and PC denotes the characteristic polynomial. Two matrices are similar if and only if minimal polynomial and characteristic polynomial is same. This is not true. Like you can take say Px to be x to the power 4 and Mx to be x square, and now take these two matrices, say 0 1 0 0 0 1 0 0, this say A. So easily we can see that characteristic polynomial is x to the power 4 and minimal polynomial is x square, and then take this one. Here also minimal polynomial is x square and characteristic polynomial x to the power 4, but both have different Jordan form. It has two blocks corresponding to 0. It has 2 blocks and 2 1 blocks corresponding to 0. So both are not similar clearly, but their minimal polynomial characteristic polynomial is same. Question number 10. Question number 10 is, so we know trace of AB minus BA is 0. Right? Let X equal to AB minus BA. So AB minus BA is a 3 by 3 matrix. Let lambda 1, lambda 2, lambda 3 be eigenvalues of X. Not necessarily distinct. Then trace, that means since trace is 0, that means lambda 1 plus lambda 2 plus lambda 3 is 0. Right? So, and determinant of AB minus BA is, determinant of AB minus BA is lambda 1, lambda 2, lambda 3, product of eigenvalues. Okay. Trace of AB minus BA cube, which is same as trace of X cube, is same as sum of cube of eigenvalues, right? Okay. Now we know equal to 3 lambda 1 lambda 2 lambda 3. This minus this equal to lambda 1 plus lambda 2 plus lambda 3 times lambda 1 square plus lambda 2 square plus lambda 3 square minus lambda 1 lambda 2 minus lambda 2 lambda 3 minus lambda 1 lambda 3. Now lambda 1 plus lambda 2 plus lambda 3 is 0. That means this is 0. That means lambda 1 lambda 2 is lambda 3 equal to lambda 1 cube plus lambda 2 cube plus lambda 3 cube by 3. That is the relation given. Okay. Now come to problem number 11. There exists R greater or equal to 1 and symmetric matrix A, M are such that for odd n this happens, right? See, A is symmetric. That means all eigenvalues are real. Okay. Okay. The given relation is, okay, then trace of A power n will be lambda 1 power n, lambda 2 power n plus lambda r power n. Right? Lambda r power n. Because it is, say, it has r many eigenvalues, so eigenvalues are lambda 1 to lambda r, not necessarily distinct, but this is true. So by given condition, it should satisfy this condition, right? Then 1 less equal to lambda 1 power n, lambda 2 power n, lambda r power n by 2 power root n is less equal to 2020. Now can you show that? So one thing is that if lambda I less equal to 1, then as n goes to infinity, this goes to 0. Summation lambda I power n by 2 power root n I equal to 1 to r goes to 0. That means this inequality cannot hold. And now it is your check that if at least one lambda 1 or lambda 2, at least 1 is greater than 1, and taking n to be even number, can you show that this doesn't hold, this inequality doesn't follow? That is your exercise. This is easy to check. As large enough n that goes to infinity, so it is not bounded by this. Right. So that is your check. You can check that. Your exercise. Problem number 12. So the polynomial px is given by this. So multiply this polynomial by 101 factorial, because this is a constant term, so it doesn't hamper irreducibility in qx, right? So multiply it. What will you get? Polynomial, you get that px equal to x power 101 plus 101 factorial x power 101 100 plus so on plus 101 factorial x plus 101 factorial. Now to p equal to 101, 101 is a prime number, right? Now use Eisenstein criteria. Each coefficient 101 divides all non-constant terms coefficient, right? And 101 square doesn't divides 101 factorial, because 101 doesn't divides 100 factorial, right? Because 101 is a prime number, so it doesn't divide. So that means by Eisenstein criteria, now use Eisenstein criteria. Eisenstein criteria p is irreducible. Question number 13. It's a general that the group of units of Zn is cyclic if and only if n equal to 1, 2, 4, p power k, 2 times p power k, where p is odd prime. P is odd prime. That means 2 power n is not of this form, hence this statement is false. And this is a number, this comes from basic number theory. Basic number theory. You can find the proof from any number theory books. Okay. Problem number 15. So say then Z to Z mod 8, this is clearly a ring homomorphism, and surjective ring homomorphism. Okay, but phi of r star is same as phi of 1 comma minus 1. It is 1 bar and 7 bar, right, which is not equal to S, because 3 and 5 also belongs to this, so it is not equal to the group of units of S, I mean Z8. Question number 15. This is a very useless problem. I don't even understand yet from my preparation that why this question is given. I mean, it's a meaningless question, because see, you can take anything, right? So take, so it is given that P is a Shilopy subgroup, right? Take G to be S3, P to be say A3, and H to be say identity comma 1. Then clearly P intersection H is trivial, and trivial subgroup cannot be a Shilopy subgroup unless trivial subgroup cannot be a Shilopy subgroup of H unless it is itself is a trivial, right? So that means it's meaningless, so it is false statement. Okay, question number 16. Let G be an abelian group. G be an abelian group and with identity element E. If this is a subgroup of G, then either if this collection say H equal to G belongs to G such that G equal to identity or order of G is infinite, is a subgroup. Then all elements of G minus identity has infinite order, or all elements of G has finite order. So if all elements of G has finite order, then we are done. But if it happens that choose an element A belongs to G such that order of A is finite, and I mean choose an element B belongs to G such that order of B is infinite, right? Then show that, this is easy exercise, show that order of AB is also infinite. B belongs to H because order of B is infinite. AB belongs to H because order of AB is infinite. Since H is subgroup, that will imply A belongs to H, but order of A is finite. That's a contradiction, right? That's how it is false. So only you need to show that order of AB is infinite. That is a very easy exercise. If order of A is finite and G is abelian is given, mind it, G is abelian. So that means AB power n is same as A power n, B power n. You can use that. That means order of A is finite and order of B is infinite. That will imply you that order of AB is infinite. Okay. Question number 17. This is also an easy one. There exists a natural number n such that x to the power n and x are conjugate for every element of x of this. So if okay, there exists a natural number n there is a natural number n such that x to the power n and x are conjugate. Okay, so in Sn this is false. Why? In Sn result, a very important result, in Sn any two elements are conjugate if and only if they have same cycle structure. Now if you have a cycle, you know how its powers looks like. Now try to solve that x to the power n and x are conjugate for every element of x. Is it possible or not? There exists some n or not? Okay, this is your exercise. It's easy one. But you have to use this result that any two elements are conjugate in Sn if and only if they have same cycle structure. That means if you write it as a product of disjoint cycles, then both have same structure. Then they are conjugate, if and only. Right. So now the question comes down that does there exist a natural number n such that for every x to the power n and x have same cycle structure? That is not possible. Why? Just try this. Why this is not possible? Okay. Problem number 18. Every non-commutative ring has at least 10 elements. Not, you can find say AB0A, AB belongs to Z2, has order 4 and is non-commutative. Just this is an example. Okay. Now problem number 19. N be a sequence of elements in 0 1 such that all positive integers n summation ai is divisible by 3. That means a1 a2 plus a10 equal to 3k1, a2 a3 a11 equal to 3k2, a2 a3 a11 is 3k2. So if you do 1 minus 2, you will get a1 minus a11 is 3 of k1 minus k2. That means a1 minus a11 is divisible by 3. Now a1 is 0 or 1, a11 is also 0 or 1. That means a1 equal to a11. If a1 is 1 and a11 is 0, that means 3 doesn't divide 1. That's a contradiction. That means either a1 and a11 both are 0 or a1 and a11 both are 1. So they are same. Similarly, you can show that a2 equal to a12 and so on. That means you can choose k to be 10. Then an plus k equal to an for all n. An plus 10 equal to an. You can easily check a2 equal to a12 similarly, right? Because a3 up to a12 is 3k3, and if you do 2 minus 3, you will get same, and so on. Right. Last problem number 20. The interior of any strip bounded by two parallel lines in R2 of width strictly greater than 1 contains a point with integer coordinates. So you can solve this problem completely by geometric intuition. So choose any line L in R2. So three things can happen. L is parallel to x-axis, 2. L is parallel to y-axis, and third one, L is not parallel to both x and y axis. So case number 1, L is parallel to x axis. That means L is this. Okay, L is this and two parallel lines. Say this is L1, this is L2, right? And it says that their width strictly greater than 1. That means this is strictly greater than 1. So that means you can always find the integer coordinate there. That means you will have 0 comma say k, which is a integer coordinate. Okay, why you will get that? Because it is strictly greater than 1, right? And any two integer I mean on a real line, consecutive to integer has distance 1. So when you have, if you choose any interval of length greater than 1, you will always find an integer there, right? So better. Okay, if L is parallel to y-axis, then same thing happen. Okay, if L is parallel to y-axis, that means the same thing happen. Then you can take any interval on x-axis, right, of length greater than 1, then you will always find a integer coordinate. Then that k comma 0 is the integer coordinate containing in the interior of this strip, right? Now if they are not parallel with x-axis and y-axis, that means this will some cut some at some point. It's maybe the here or there, anything like that, and this is say another line. Now it says that width is greater than 1, that means this length is greater than 1, right? This length is greater than 1, and it is easy to check that this length is always greater than this length, because these are not parallel. Sorry, these are parallel, but this is not parallel to any of the coordinate axis. So this length, if I give it say L, and this length if I give it to M, that means L is strictly less than M, right? And on this line, so if L is greater than 1, that means M is also greater than 1, and then that is also the same reason as above. This has always a integer coordinate, so you can take 0 comma some k or something. Also you can take in this way also, you can also take this part also. So this part also you can argument, you can give an argument 0 comma k, as well as you can find some n comma 0 also, that is also an integer. So the main thing is that there always exists some integer coordinate since the width is greater than 1. Okay, thank you.